way our brains react to actions, whether they respond more to what we do or simply how we do it, remains one of the most intriguing debates in neuroscience today. And here's where it gets really compelling. Recent studies are challenging the old-school notion that our motor control is straightforwardly mapped to specific body parts. Instead, new research reveals a more flexible, action-centered design that could reshape how we understand movement, learning, and recovery. For decades, the dominant idea in neuroscience held that our motor cortex is organized like a detailed body map, an idea illustrated vividly by the so-called motor homunculus. According to this classic view, distinct brain regions correspond directly to controlling specific limbs, hands, feet, face, and so forth. This arrangement suggested a rather rigid structure, with the brain's physical layout mirroring our body's anatomy. But what if this entire map is too simplistic? What if instead the brain's organization prioritizes the type of action being performed, like grasping or walking, rather than which body part is involved? A recent groundbreaking study from Georgetown University invites us to reconsider very fundamental assumptions about this organization. Led by Assistant Professor Dr. Striem-Amit, the research explores whether the brain is naturally inclined to represent the same fundamental actions regardless of the body parts that perform them. To probe this idea, the team studied individuals who are born without hands, people who have learned to use their feet for complex tasks typically performed by hands. These individuals serve as a natural experiment. This technology visualizes real-time brain activity while participants perform a variety of tasks involving tool use, object manipulation, and movement. What's truly fascinating is that the brain areas usually involved in hand-related tasks, like grasping objects with a tool, show heightened activity even when these individuals use their feet for the same purpose. This suggests that certain brain regions encode the nature of the action itself, rather than being strictly tied to a specific effector like the hand. This idea of an action-focused neural organization opens up exciting possibilities. It hints that the brain might be optimized for adaptability, able to reorganize and assign different effectors to the same action based on need. Such a flexible system could be critically important during early development, rehabilitation after injury, or in adapting to bodily differences. It shows us that our brains may be more abstract in how they represent movement, focusing on the goal or function of an action rather than the specific limb used. However, this plasticity isn't uniform throughout the entire motor system. The primary motor cortex M1, which has traditionally been seen as the final command center for precise movements, remains surprisingly steadfast and specific to body parts. Even individuals who use their feet for years didn't exhibit significant reorganization in M1 for foot-based tool use. This points to a fascinating division within the brain. Some regions are highly adaptable and action-oriented, while others retain more rigid, body-specific maps. These findings could revolutionize how we approach neurorehabilitation after strokes or limb amputations. If the brain houses flexible, action-based motor maps, then therapies could be designed to stimulate and harness these regions, possibly making recovery more effective, regardless of which limb is affected. Additionally, this research has implications for prosthetics and assistive technology. Instead of focusing solely on mimicking limb-specific movements, devices could be designed to interface with the brain's abstract action representations, offering more natural and adaptable control. Interestingly, this concept aligns with observations in sensory systems as well. For example, in individuals who are blind or deaf, the brain regions usually dedicated to processing sight or sound are often recruited for other functions, demonstrating incredible neuroplasticity. Similarly, this action center approach suggests that our brains are fundamentally designed around how we interact with the world, not just which body parts we use. Early childhood appears to be a key period for this flexibility. Dr. Striem-Amit mentions that certain brain areas are most malleable during infancy and early years, influenced heavily by experience and interaction. Understanding these critical windows could lead to innovative therapies, for those born with limb differences or who acquire injuries later, helping them develop new movement strategies and skills. The study included inspiring human stories like Alvin Law, a man born without arms due to thalidomide exposure. Alvin has spent a lifetime mastering manual tasks with his feet, exemplifying the brain's remarkable capacity for adaptation. While Alvin himself finds prosthetics unnecessary given his unique abilities, he acknowledges that this research fuels hope for future solutions that could assist others facing different challenges. All in all, these discoveries suggest that our motor system is far more dynamic and complex than we once believed, comprising multiple interconnected networks that operate at varying levels of abstraction. Primary motor areas preserve detailed, limb-specific information for precise control, but other regions encode broader, goal-oriented actions, coordinating our interactions with the environment with extraordinary dexterity, even amid bodily differences. Presented in the prestigious Proceedings of the National Academy of Sciences, this cutting-edge research from Georgetown University opens a new chapter in understanding movement control. It pushes us to think beyond evolutionarily conserved body maps and consider the brain's capacity for flexible, action-centered organization. The implications extend well beyond academia, potentially transforming rehabilitation practices, prosthetic design, and our overall view of human neuroplasticity. In essence, this work challenges us to reconsider whether the brain's core wiring is dictated solely by our body schema, or, if at a deeper level, it's organized around the fundamental actions we perform, no matter which limbs execute them. What do you think? Could this flexible, action-based model be the key to unlocking more effective therapies and technologies? Or does it threaten to undermine everything we've long believed about our brain's structure? Drop your perspective in the comments. Let's discuss how far this idea could take us.